Hello. All right. Happy Saturday, first off. Congratulations to everybody that just took the mock exam. It was tough, not an easy test by any means, but when we get our scores back in early April, we'll get a good sense of where we're at in preparation for the AP exam in May. The big things that we need to review are definitely going to be waves, circuits, and springs, and we have time reserved to do that, but in order to ensure that we have ample time in the future to review, I also want to make sure that we spend enough time getting through rotational energy and rotational momentum. So for that, I'm going to push the test back one more day. As you can see in the email, that here's what your calendar is going to look like. You're going to have Monday. It's going to be the rotational energy problems that are due, which are the ones that you were given at the Saturday, a little bit earlier today, and the rotational energy problems that are in your packet, RMM 4 problems as well, the ones that you haven't finished. This is what you're doing for Monday. You're also going to have a quiz that's going to be similar, not a free response question, one that's going to be similar to the questions that you've been given to solve. RMM 4 quiz Monday as well. Tuesday, you guys are going to be learning about angular momentum. We're going to be doing demos in angular momentum. Your homework from Monday to Tuesday will be to watch videos and do questions. That way we can review angular momentum in class, and we can spend a bulk of the class time actually going over the problem set, so review problem set. Picture, then we're going to go
over it, and then you're going to make changes and all that for corrections. Okay, and then Wednesday is going to be the actual test, which will combine RMM 4 obviously, and then RMM 5, and we'll go over 1, 2, and 3 on this day as well, as we not only as we review the problem set, but also we go through some FRQs. Okay, that's to give you a little bit of heads up of what we're doing this week. Now today in particular, I want to make a set of videos that are going to help you solve the problems you have due on Monday for RMM 4. And so these problems are the ones that are, as I mentioned, all the problems in your packet. These 5 problems we already did 1, 2, and 3 in class. And then the questions that I handed out today. And so I think a really great problem to start us off on this is this first problem. Ball rolls down a hill without slipping. Okay, that means that we have to consider rotational kinetic energy. Down a 0.45 meter tall incline. If the ball started from rest, at what linear velocity will the ball be traveling at the bottom? Whoa, okay, so there's a lot of different stuff going on here. So the first thing I want to talk about is actually what does it mean when it says without slipping? And I'll post another video in the email, a link to another video in the email that I think explains this concept really well. What I'm going to do is do a quick review, or a quick introduction to this idea. This is a coaster. It's a coaster that represents the college that I'm from, that I went to school at. And it is also a circle, which means that it can rotate. Now, we've talked about objects that have translational kinetic energy, right? And we've talked about objects that have rotational kinetic energy. That is a straight line. I know that I have to tell you because it definitely doesn't look like a straight line. Now, if this object slides across the surface, that's slipping. Let's do this. Slipping. That means that this object, this coaster, is literally the circle has some translational velocity to the right. At this point, there's going to be friction, right? But the friction is continuous. Friction is opposite the displacement as well. So friction is going to be doing negative work. It's going to be taking away energy, drops energy. It's going force of friction is going to be taking away energy from this system. It's also going to be doing this because, I mean, not only does it take away energy due to the friction, but also like this. That's how car brakes work, ABS. What was I going to say? Oh my gosh, I forgot what I was going to say. Anyway, the force of friction is, I remember. What kind of friction? It's moving. Kinetic, baby. F kinetic, right? Now, let's talk about rolling without slipping. Rolling, rolling on the river. What does that look like? If this coaster were to not slip, that means that it's not going to slide. This is slipping. Rolling without slipping, something like this. It's kind of just like rolling that we were talking about before. Like the type of rolling that we were discussing. Rotational energy. That is rolling without slipping. Right? Now, the reason I mention this is to bring up one really important point. So if we draw this, there's some velocity here, some velocity here, there's also some velocity here. But what's really interesting is that this is translational, and these are angular. Of course, there's still translational velocity here, and here, and here. But on the outsides, you also have angular velocity, and on the inside, you have angular velocity as well. So there's omega and v. It has both. What that means, however, is that this force of friction is actually not acting to the left as much as it is acting actually, that's not true. Sorry. The force of friction is still acting in this direction. What is different, though, is this displacement. So the displacement of this point is always going to be up, the one that's rotating about the bottom. And so as this point rotates up, we know that friction is not going to be actually taking away any energy. Force of friction will not be taking away energy, right? The force of friction will not be taking away energy because as this object moves, of course, friction is going to be sliding, or this object is going to be sliding against the surface. There's going to be displacement here, and then the force of friction is going to be opposite that. That's negative energy, or negative work. What's happening here is this point is actually moving up, right? Every time friction acts, the point itself is rotating up. Friction is never going to take away or do negative work from this object that's rolling without slipping. Now, we also know that technically at every moment, this bottom part is instantaneously at rest, right? Like this bottom part every second, technically, this bottom part is at rest with the surface of the Earth. And the video that I'm going to post another link to goes over this really well and explains this concept with some visual examples, which I don't have right now. But that means that the force of friction here is going to be static. You're going to have static friction. So big things to remember: rolling with slipping involves kinetic friction and takes away, and where kinetic friction takes away energy from the system. Rolling without slipping involves static friction, where friction does not actually take away any energy from the system. In fact, friction is required in order to get the system to roll. You need to have friction, because otherwise this thing is going to the object to stick.
Now, what does this even mean for problems that we want to solve? Let's take a look back at this problem. A ball rolls down a hill without slipping. Okay, so we have to consider rotational kinetic energy. That makes sense because the object is actually rotating now. So I'll solve this problem out on this paper right over here. And so we already started talking a little bit at the end of class on Friday about conservation of energy. Let me make sure that you guys can see. Let me slide this up a little bit, and then close that. All right, cool. We started talking a little bit about conservation of energy, in particular for rolling objects. And so if we're looking at a ball that rolls down a hill, 0.45 meter tall incline, first off, we need to draw a picture, without a doubt. Say that this is a 0.45
meter tall incline. Right? We've got a ball. We're assuming this ball is going to start from rest. This is initial, and then pew, final. Right? And we know at the end, not only, because it's rolling without slipping, we know that not only does it have some translational velocity, but it also has angular velocity. Right? And so we have to consider both translational and angular velocity at the end. Now, the question is, how fast is it going to be going linearly? Right? It's asking me about the linear velocity. All right, so in order to set this up, we already know that objects that have a lot of I are going to have, or a lot of inertia, are going to take a lot longer to go to the bottom. How do we know this? We did this, we proved this using conservation of energy. So at the top, what kind of energy does it have? It has potential, right, mgh. At the bottom, what does it have? If the height is 0, it has kinetic energy, translational, but it also has kinetic energy rotational, right, the red velocity. So that means that our equation is going to look a little bit like this. 1/2 mv squared, 1/2 I omega squared. So then we have potential, I'll just write it out like this. mgh is equal to 1/2 mv squared plus 1/2 I omega squared. All right, word. Now, we know that, we know that this object has a mass that we're given. Oh, actually, we're not even given the mass, but well, hold on. Let's see what happens when we don't even we don't consider the mass for now. We have this v here, and we have an I and an omega. The first thing I want to do, because I want to get it into the form of linear velocity, I want to find that. I want to plug in what I know about I into this expression right over here. So according to the problem, if it's a ball, I would consider that a solid sphere. We're not told whether or not it's a hollow ball or a solid ball, but let's assume that it's a solid ball. And this is something that should have been included into the question. A solid sphere, so that I is equal to 2/5 mr squared. And this is just the I for a solid sphere. Now, another nice thing is that we always know that omega is going to be equal to v over r. That is super helpful, because if you notice here, that v over r is going to be squared, and so we're going to have a v squared over r squared, and we're going to have an r squared over, oh my gosh, things are going to cancel out. This is going to be great. Let's get cracking with some algebra. All right, so we know that mgh is equal to 1/2 mv squared plus 1/2, oh my gosh, I'm not going to have enough room, 2/5 mr squared times v squared over r squared. So r's cancel out here. The m's cancel out from the whole thing. Look at that. There's one m in every single term. So what happens is we're left with something pretty nice. GH is equal to 1/2 v squared plus, cancel these ones, cancel out those 2's, 1/5 times v squared. Did I do that right? Yeah, I think I did that right. All right, cool. Now, this is the trickiest part because it's algebra. 5/10 plus 2/10, 7/10. Yeah, okay, word. GH is equal to 7/10 v squared. And so then, whoa, you lost mass. Huh. So then v squared is equal to 10 GH over 7, and then I'm going to slide over to this side. V must be equal to the square root of 10 GH over 7. I'm not going to plug in the numbers. I want you to follow the work here and then solve for V in your own paper right over here. Figure out what the linear velocity is going to be for the ball at the bottom. We also know something that's nice is that the mass does not matter, right? Just like conservation of kinetic energy, the mass here does not matter for the ball. What I want you to do is solve this problem. It's pretty much the same. I mean, it's that problem. Number 2, consider the objects that are in motion and think about where potential energy is being converted into rotational kinetic energy. Okay.
This problem requires you to... This problem is a calculation involving rotational kinetic energy. You guys can do that. And number 4, V spicy, is going to be a problem similar to the one that I went over on this page. That's going to be problem 4. It's just kind of like the opposite, because you're going up the hill, but you guys can do that. Problems 4 and 5 require considering objects that are rolling without slipping. This one's actually also similar to the problem 1 that I just gave you. So all of these problems are excellent problems to practice and are all fair game for your quiz on Monday. In fact, I may just choose one of the, I will probably just choose one of these problems and change some numbers and ask you to do that. All right. If you have any questions, please let me know. As always, you can text and or email me. Remember, big things. I'll just write them right over here. Always sketch 2. Write law of conservation of energy, loco E. 3. Sub in for I and V, I and omega rather, and 4. Solve that bad Larry. Alright, let me know if you guys have any questions. I think that is pretty much how to do all these problems. Alright. Nope. Deuces.